quadratic residues, and it's probably something I'm not going to see in other courses. So the question is like this. And the funny thing is, it's very easy to solve this equation. So this is, of course, consequence modulo p. So what can we do with such consequence? The difference of squares. In fact, b squared minus a squared is, or maybe a squared minus b squared is equal to k. Or I can write it as a minus b times a plus b. So we can take p. And now I want to count how many solutions a, b other to this equation. Well, I can make a change of variables. I hope that most of you have taken some linear algebra course and know that if instead of a and b, I will go to new variables, x and y. X is a minus b, y is a plus b. This change of variable is inverted. I can go back and forth between the variables a and b and x and y. Because, well, I can just write down what a and b are in terms of x and y. A is x plus y over 2, and b is y minus x. So there is no problem with changing the variables this way. I'm not losing any information. But once the equation is written in this way, xy is equal to k modulo b, it's really obvious what are the solutions. I mean, for every x, which is not equal to 0, we get one solution y. So there are a total of p minus 1 solutions. Once again, the reason is for every non-zero x, I have a solution. X, comma, a over x. And how many non-zero numbers are there? Modulo p, well, p minus 1 numbers. So basically, it's very easy to count how many points, how many numbers a, comma, b satisfy these conjugates. Well, that's almost the answer to the original question. In the original question, I didn't want to count the pairs a, comma, b. I wanted to count, well, the numbers themselves, the quadratic residues themselves. And for every here in this equation, I have a freedom. Choose instead of a minus a, instead of b minus b. And every time I have something like this, and using y here and y here, that's not good. Oh, here I want to ask, well, I want to start with a quadratic residue, and every quadratic residue gives me two ways of writing it as something squared. I can choose b and minus b. And for this b and minus b, once I shift it, I can once again write it in two ways, a squared or minus a squared. So basically, for every number, for every solution here, I have 4 solutions here. So the answer to the original question the answer A. So if A is the number of such quadratic residues such that A plus K is also a quadratic residue, satisfies 4 times A. Every answer to this question gives me 4 answers to this question. Is equal to p minus 1. Well, almost. It would have been like this if, well, if a and minus a were always distinct, if b and minus b were always distinct, and if quadratic residue was always, well, there was no difference between quadratic residue and b squared. Well, quadratic residue is always non-zero number, so there is, well, some small details left out. Here, it's not exactly that every answer to this question gives me exactly 4 solutions of this equation. Well, sometimes, for example, if b is equal to 0, this is not a quadratic residue. So basically, all the solutions here correspond to solutions here, besides the ones where b is equal to 0 or a is equal to 0. All other ones do correspond to solutions of this equation. So there is a correspondence. It's not really exact. It's exact, well, if a and b are both non-zero. Other solutions where this correspondence is not exact, when a is equal to 0 or b is equal to 0, well, it depends actually on k. It does depend on k, unfortunately. And so let's see. Is there a solution when b is equal to 0? Is there a solution of such that k is congruent to some square? Well, there is a solution if and only if k is a quadratic residue. Is there a solution with a equal to 0? Well, yes. Well, is there a solution of k equal to minus b squared or minus k equal to b squared? Well, yes, if and only if k minus k is a quadratic residue. So here it is minus, well, minus 2 with k or minus k is quadratic residue, and minus 4 with k n minus k is quadratic residue, and so minus 0 with k and minus k are quadratic non-residues. So there are some small details here that, well, something does depend on k a little bit, but what's good is, well, there is a special case that actually doesn't depend on k. So here I have to decide whether k is a quadratic residue, whether minus k is a quadratic residue. There is a special case when p is congruent to 4 modulo, congruent to minus 1 modulo 4. So first of all, that's the answer to the general problem. How many answers are there? But there is a special case. If p is congruent to minus 1 modulo 4, then minus 1 is quadratic non-residue. So k is a quadratic residue if and only if minus k is quadratic non-residue in this case. So this should be clear. So if you are prepared for the quiz, you should understand both statements. Why is minus 1 quadratic non-residue modulo such a prime? Well, that's just, yes. I mean, if p is congruent to minus 1 modulo 4, then you know when is minus 1 quadratic residue. If and only if p is congruent to 1 modulo 4. Here it isn't, so minus 1 is quadratic non-residue. Okay, minus 1 is quadratic non-residue. So if k is quadratic residue, then minus k, as being the product of quadratic residue and quadratic non-residue is quadratic non-residue, and vice versa. If k is quadratic non-residue, then the product of minus 1 and k is a quadratic residue. So in this case, we always get the answer for a is equal to k minus 1 minus 2. Exactly one of those is a quadratic non-residue. So we get a funny property. So property of quadratic residues modulo e, which is congruent to minus 1 modulo 4. The property is like this. If you take the set of quadratic residues and you shift it by any number k, in the intersection you get, so in the intersection of the set of quadratic residues modulo p and its shift by k, there are exactly minus 3 over 4 numbers, elements. So half the numbers modulo p are quadratic residues, half the numbers are in any shift of quadratic residues. In the intersection there is exactly 1/4 of those numbers. It's really some non-trivial combinatorial property, if you think about it. But let me show you one very funny example. When p is equal to 7, quadratic residues are 1, 2, and 4. 1 squared, 3 squared, and 2 squared. Shifts of quadratic residues. So shifts of quadratic residue. Let me try to include. So the shift is set. Let me shift it by 1, 2, 3, 5. Shift by 2, 3, 4, 6. Let me continue. 4, 5, 6, 0. Here 4, 5, 6, 0, 1. 0, 1, 2, 3. So these are the shifts. 1, 2, 4, 2, 3, 5, and so on. These are the quadratic residues, and these are the quadratic residues shifted by different integers. I know that if I take any two sets here, in the intersection there is exactly one element. For example, here and here, 3, 4, 6, and 6, 0, 2, there is exactly one element and so on. 6. You can try with any pair here. There is a funny picture associated with this. You can draw 7 points like this. 1, 2, 4. Connect them by line because I want to set here. 2, 12, 4, 4, 2, 6. Connect them by line. 6, 5, 1. Connect them by line. What else? 4, 5. There is 4, 5, 0. Connect them by line. 2, 0, 6. 3, 0, 1. Connect those by line. And finally, 2, 3, 5. There is 2, 3, 5. Well, let me say that they're also connected on the line. But it's rather a circle. What's special about this picture is as follows. If you take any two lines in this picture, well, in the circle here is kind of pure line like this, they intersect in exactly one point. If you take any 2 points, they lie on exactly one line. So in this picture with 7 points, you have kind of very, very funny thing happening. Every 2 lines intersecting a point, every 2 points can be joined by one line. So it is kind of geometry. It is usual plane, kind of, it has the properties of the usual plane. Every 2 points can be connected by line, every 2 lines intersect at a point. But it has only finitely many points, 7 points. And this plane comes, from these things, from quadratic residues. So there is a whole branch of mathematics which is about finite geometry, and you see that this finite geometry, funny kind of geometry with only 7 points maybe, there are larger examples of course, but this is still finitely many points, is very, very much related to this number theory, these quadratic residues, quadratic reciprocities, and such stuff. Okay, so now let's get at this. This is, by the way, not for example anyway, so it was fast and few details, but still, I wanted to show that it's cool.